Catalytic hydrogenation. This is a form of addition reaction. Just to review really quickly, an alkene has a double bond. It reacts with some sort of reagent that has two components, an X and a Y, and you end up with the substituted alkane. Let's take a look at what this looks like. Here you can see our alkene. It's got a methyl group, an ethyl group, a T-butyl group, and an isopropyl. Now the X adds to one of the sp2 hybridized carbons and the Y adds to the other. In this example, I've got the X adding above the plane of the molecule and the Y adding below. This kind of stereochemistry is called anti. Now in this picture down here, I've got a different kind of stereochemistry. This is syn. Notice both the X and the Y add above the plane of the molecule. I could also have them both adding below. But these are the two different kinds of stereochemistry for addition reactions, anti and syn. And catalytic hydrogenation is syn. So when you have syn-addition, there are two possible products. One from the substrate adding above the plane of the molecule, that's here. You can see that both of our hydrogen atoms are on wedges, meaning they both came from above the plane of the molecule on the left, the substrate. So if you get rid of the hydrogens, because we don't draw those normally in bond line structures, this is what your product looks like. The other possibility is that the hydrogens add from below the plane of the molecule, and that's shown down here. Notice both of the hydrogens shown are on dashes, and so if we get rid of the hydrogens there, this is what you will see. So the product on the bottom is the one where the hydrogen added from below. In terms of what this looks like, your reagent is H2 and your catalyst is a metal like platinum or palladium doped nickel. You can also use something called Wilkinson's catalyst, which uses tris-triphenylphosphine rhodium chloride in solution. Let's take a closer look at catalysis. One of the biggest parts of the activation energy is breaking an HH bond, which is 436 kilojoules per mole. That's a strong bond. So looking at the microscopic level, here's the metal surface, these gray atoms, and you can see that there are a bunch of hydrogen atoms bonded to it. Now hydrogen likes to be a molecule, H2, but when an H2 molecule collides with the metal surface, the molecular orbital sort of overlaps with the orbitals in the metal, and it breaks the HH bond. So as long as the hydrogen atom is adsorbed onto the metal surface, it's free to roll around. So rather than having 3 H2 molecules here, we've actually got 6 hydrogen atoms. Now, look at the alkene. Here, you see this dashed line going from the pi bond of the alkene to the metal surface. That's to indicate that the pi bond of the alkene also overlaps with the orbitals on the metal surface. So, what's going to happen is this hydrogen atom is going to bond, this hydrogen atom here is going to bond with this half of the molecule. So this carbon will now have a bond to hydrogen and will no longer be participating in the pi bond. So now you can see the right-hand side of the molecule was released because this hydrogen replaced the pi bond. Okay. The left-hand side of the molecule is still bonded to the metal, and it's going to interact with another hydrogen atom. That hydrogen is going to replace the bond between the carbon and the metal. And sure enough, that's what you can see here. Your alkane that was formed has been released. But this is why you get the syn stereochemistry.